Is very live. All right, everybody. Today, well, I'm still waiting to hear from a local university lab to get access to an interferometer to conduct our vertical Michelson-Morley's experiment. So, according to the scientific method, we need to make a prediction before we run the experiment. Running the experiment and then explaining it, that's not the the gold standard of a scientific method. We need to make a prediction what will happen during the experiment, and then we conduct the experiment, and then we compare expected to actual, and calculate errors and see that we have statistically significant validation. Then with the goal, we are golden. So yeah. All right. So let's try and predict it. It shouldn't be that difficult. I don't think it should be that difficult because we know. So the first thing we need to do is let's figure out the equations and then plug in like nominal numbers, like more or less, and then once we plug in our more or less numbers, what do we do then? Okay, and then we can go back and actually do a more accurate calculation and redo it. Can always redo it with more and more accuracy, but it's not critical. I mean, the more accurate you are, the better, obviously. All right, so how would we do this? Let me the first thing that I should always remember is to copy the link to the room from Discord into oh, I didn't see that. Let's check YouTube audio. Okay, audio is good. So let me paste the link to the room so that anyone can join me on the Discord. I don't see any messages showing up. Oh, there it is. Everything is good. Let me pin message. All right, that's good. The next step is here is the link. So the next message would be to do the calculation. So let's pull up a whiteboard. We need a whiteboard. La 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 la. La 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 la. What's this? Michelson-Morley fixed. Instead of fixed, I would just call it vertical. This is the vertical. What just happened? So this is going to be the vertical Michelson-Morley. We can't have all the letters, so Michael. We can just do Michelson. Vertical Michelson-Morley. There you go. So let's try and get an accurate prediction. Let's try and get an accurate prediction. An accurate prediction. Okay, so what is this going to look like? So basically, this is the Michelson-Morley, the vertical experiment. Here is the ground. We use 3 lines in engineering to say this is the ground. All right. So what are we going to do? It's going to be a normal thing, normal interferometer, but everything needs to be on this thing, and we need to be able to rotate it because I don't think. I mean, we could calibrate. I don't think there's anything. I don't think we can calibrate it. From what I've seen online, you can't really calibrate it. You're always going to get an interference. From what I saw online from these experiments, an interferometer always gives an interference. It's just that when you move it, the interference changes. So that's what Michelson-Morley expected to get, but horizontal. Of course, you're not going to get it according to a proper theory of gravity, that the ether flows into the center of the earth, towards the center of the earth. So, okay, what will the interferometer include? There's going to be a source of light. Let's say we'll use a laser. So the laser will fire this way. We're going to have a half mirror here. So the light, one beam is going to hit this thing. So half of it will continue straight. So half will continue. And here we're going to have another mirror. This is going to be a full mirror. This is a full mirror. So this will go back. It will hit here and go back. And get reflected. Half will go into the emitter, which is meaningless, and half will go up. And here at the top, we're going to have a display. This is a display. We're just going to see, well, the laser beam. So, right, it's a laser pointer. You don't expect to see anything other than just the laser pointer, the point that the laser beam makes when it hits the wall or hits anything. You just expect to see basically a big dot, a big red. Usually it's red dot. Okay, that is one signal. The other signal. So right, it's halfway mirror. So the other signal, it's going to go down, and at the bottom we are going to put another full mirror that will reflect back, and we'll use, I guess, can't use white, green we've used, so I guess purple maybe, I don't know, it's going to be difficult to distinguish. There's not too many colors. Yeah, the first one has everything. It has the RGB. R, I think G and B. And yellow we've used everything. So I don't know what to do now. Okay, we'll try purple. So we'll go from here. So this will go, basically it's a half mirror. Well, half again will go back to the emitter, which is meaningless, but half will go to here. And here we're going to have either no interference, constructive interference, or destructive interference. Or, from what I've seen online, you're just going to get a circle and a circle and a circle. So there's always going to be an interference. But then, we'll use tape to see where the circle, one of the concentric circles is. And then we're going to, let me get a sip of water. And then we're going to rotate. That's not how you rotate. We're going to rotate this device and watch the signal. Keep watching it. And as we rotate, I expect it's going to appear as if we're moving one of the mirrors, or, the signal should change. And the concentric circles should move in or out. Something should happen to the signal as we rotate. So we know, as far as I know, which is always the faster. So since we are assuming that the ether is moving very fast, about 6 million meters per second, we should go back and do a more precise calculation. It's approximately 6 million meters per second. So this is the direction of the ether. This means that this will be very fast going down and very slow going up, whereas this is almost not impacted. The horizontal is almost unimpacted. So it's going to be normal this way and normal this way, except for because of this motion, it's going to get deflected. So let's use green, this color. So let's say it's going to, the wave is going to hit here and go here. And because of this extra distance, it's going to slow down a tiny, tiny bit. Whereas, well, they're both tiny, but this one is supposed to slow down just a little more. That's what I've seen. I never looked at the actual calculation, so I don't have an opinion about it. My intuition was, hey, there should be no difference between the two. But apparently, when you actually do the actual geometry, this is a little bit slower, and because it's a little bit slower, so you're gonna get an interference. But when you rotate, so let's now rotate this thing. Let me look at it. Let's rotate. How would we rotate? So let me take this thing. Let me take this entire, yeah, we can take the entire apparatus except for the direction of the, except for a bunch of things. Oh, we can't. All right, let's try this again. Let's take everything. I don't care. Let's say copy everything. We're going to copy everything over to here. That's not what I wanted. That is so dangerous. Imagine I had something private to paste. Wow, that is dangerous. Très dangereux. Très dangereux. So how do you copy? What is this? Is this copy? Okay, it just copied it. That's good. So now we're just going to move it over to here. That's good. But I already want to rotate. Oh, there's no way to rotate? What is this? What is this? I don't know. What is this? I don't know. How can you rotate? No, there's no way to rotate. There's no way to rotate that. That's not good. That's not good. Okay, we'll deal with it. All right, so let's remove. Well, I don't want to remove it. Let's say we rotated it. Since we can't rotate, we're going to have to draw it, redraw it with a rotation. So I would just remove planet Earth, remove it, and remove, since we cannot rotate, so remove the ether. And let's say we rotated it, so now the Earth is going to be in this direction. This is the Earth after we rotated. So the ether is now flowing perpendicular towards the center of the Earth. This is the ether. And if this is the ether, so what do we expect? Let's remove the previous expectations. So what do we, I guess we can remove this. All right, what do we expect now to happen? So this is the ether. So now this is going to be, right? So this is going to be less of this is going to be less impacted, and this is going to be more impacted. So they might be impacted just the same. So these two, right? So they would be impacted just the same. That's right. That's what should happen. So before this was impacted more and this is less. Now they're impacted just the same. Basically, if they're impacted just the same, so we expect this shift to have changed. And this will cause the circles to have moved relative to each other, inwards or outwards. So if we move this way, now we expect right? Before this was faster, but now they're just as fast. So this was faster, so you had the wave reach over here, but now it's going to be a little bit slower relative, so it's going to be a little before, but this is a little faster, so it's going to be a little forward. It really depends which is the inner, which is the outer. All we see is just an interference. We don't know because it's the same color, unless we change the color. So if this mirror reflected only a certain color, if we had a white laser and we could reflect, let's say, red and blue, then we would see, but then I don't know what kind of interference we would get. That would be different frequency. That would completely destroy the experiment. So you actually want you want a perfect reflection. You don't want to change the frequency. Oh, it comes out as one specific frequency. That is what a laser is. You can't have I don't think you can have a white laser. A laser is one precise frequency. That's basically almost the whole point. Laser doesn't have the word frequency in it, or nor wave. But the whole point is that it's designed for exactly, I think the size of the laser is with whatever light gets bounced back and forth. This is literally the wavelength. There's two mirrors. A laser is just two mirrors with a light source in the center and a hole, just a tiny hole on one side. That is all that a laser is. So the waves, the back and forth waves, I think it basically creates an echo, a self-amplified echo or something like that. It bounces, and then some of it, once it's like in a harmonic, it's like you get a harmonic sound. I think it's like similar to breaking a glass or something. Anyway, I don't know how a laser works. So, and then you get the light out. It has to be of one frequency exactly, and that's okay. That's the point. Okay. Anyways, as we rotate it this way, we expect one of them to become faster, one of them to become slower. So we expect the two wave, I think, crest wave troughs, and whatever, like the high point and the low point. So if before they were together, well, the one is going to shift. Okay, so the question is, let's say we rotate, let's say something like this. This is basically 45 degrees. This is a 45 degrees rotation, right? This is 45 degrees. So we want to be able to predict, like, how many times should the circles go, into each other? How many waves do we expect to go through, as, let's say, per 1 degree? So each degree, how many waves, or what part of a wavelength, what is the ratio? So usually what they do with an interferometer, they just change one of these mirrors, they move one of the mirrors, and they see wave how many wavelengths per micrometer. And then that's what they do. So ours is going to be a little bit different. We're going to rotate. So we are going to do degrees. The whole point is degrees, or wavelengths per degree. So for every degree, we could rotate very accurately or very roughly 45 degrees, 90 degrees. We could just do, okay, over 90 degrees, how many wavelengths do we expect, or how many half wavelengths? Because every half wavelength is right. The one of the concentric circles are going to jump the tape, move through the tape, just like they showed in the video we watched yesterday. Okay, there's so much pressure because my chick is not talking to me. It's so distressing. It's so distressing. It's like my heart is devastated. Absolutely devastated. Anywho, so okay, that's what we need to do. So can we do that? So every degree, I think usually it's easier to talk in radians for some reason. We'll come back to this. Radians is just a bunch of degrees. I think a radian is like 180 degrees or something. I don't know. What is a radian? Or what is a radian? A radian is pi over 2 degrees or something? Or pi degrees? I don't know. I don't know what we'll come back to see how we'll do the calculation. No one is watching us. We're all alone in this god-forsaken universe. Let me check the audio because that usually relaxes me. Yes, it's good. The audio is good. The audio is good. So the next step is to start doing the calculation. How do you do the calculation? Why? So for every degree, right, this motion, it should make this faster. This should be faster and this should be slower. By how much? Well, let's do 90 degrees. If we think about 90 degrees, they should just complete symmetrically shift towards with in reference to each other. So this used to be the slower one. So before this was slow and this was relatively fast. Now they're the same speed, but at 90 degrees they change places. So this one would move over here and would become slow, and this one would move over here and become fast. But we need the ratio. Do we need the ratio? Is it important to know the ratio? Or is it enough to just know that they're changing places? Well, we need to know, we first of all need to know, given a certain velocity of the ether, what, right, at zero, if the velocity of the ether is zero, you expect nothing. But as the velocity of the ether increases to the speed of, at the speed of light, there's no signal. No, just be, okay, so, um, it so so as we increase this speed, what yeah, we need to do, we need to actually look at the calculation. We need to do the actual calculation. Now there is no length contraction because length contraction is just an optical illusion. Obviously, that goes without saying. So of course that's wrong. I mean that in itself, I'm tired of saying that this is a Nobel Prize because there's so much wrong in relativity and in modern physics that I wouldn't know where to begin. There's just wrong is it's no longer wrong, it's just garbage. I would say it's the most garbage theory ever invented. I don't know. I know very little about it, but I was listening to a YouTuber, the physics asylum. So he says length contraction is real. So he says, he asks himself, what, it really compresses? He answers himself, of course not, but it's real. So, and this guy has like 600, it's one of the biggest, no, 600,000 people follow him, and all the comments, oh, thank you. Thank you, Jesus. You helped me understand. I took a whole course. I never understood anything, but now I heard you say, now I understand. It's so clear. It's so clear. What's so clear? The guy in the first syllables he uttered, he completely contradicted himself. What is clear? Is everyone insane? Did I forget to take my crazy pills this morning? Am I insane? What's going on? And all the comments are so positive. Not a single comment says, Jesus Christ, what's going on? Why are you contradicting yourself so explicitly? And why does it keep coming? Why am I deja vuing the emperor's new clothes? This is supposed to be physics. It's the most accurate theory. It's the most accurate. No other theory is so accurate. How can you say it's accurate? It's not. It's not a theory. It's nothing. It's garbage. Complete and utter garbage. It's length contraction is real. It's tested. It's real. What? It really compresses? Of course not. But it's real. It's absolutely real. It's real. It's real. How real is it? Oh, it's absolutely. It's not. There's no actual compression. Oh, but it's real. It's real. Trust me, bro. It's real. I'm telling you, totally telling you, it's totally real. All right, whatever. Not even gonna show this to you because I don't want to waste my time, your time. Enough is enough. We gotta put a stop to this nonsense. This is a disaster. This is this is the destruction of civilization. Terrible. Absolutely. This is not even, this is a betrayal of trust. These people that call themselves, physicists and scientists, you make YouTube videos. Was I one of them? I think I was one of them. I used to repeat this nonsense. So I'm just as guilty. So are we really guilty? Was I really guilty? I mean, they think they're doing their best. So, like, but government, evil. That's evil. Like, if you ask people who commit evil, they'll tell you, "Hey, this is like Stalin. He thought he's the most righteous person in the universe. He died penniless. So he thought he's just the best thing since sliced bread." That is what makes it so dangerous. They don't see that they are evil. It's like you can't see that you're the ether because you are the ether. How can you see that you're the ether? How can you see that? You cannot. Anyway, so we got to fix it. We have a chance to fix. Let's fix. We got to do the actual geometry. We have to do the actual geometry. We're not going to get away, or we can watch a YouTube video where they do the geometry and just check their math. Um, Maybe I should try it, because I've listened to it so many times. Maybe I should try it. So the question is, given the speed of the ether, which is the same as the motion, the relative. This is basically relative motion. Is it? Is this relative motion? I don't know. But there's plenty of videos where they do this calculation. Should I do it myself or should we watch? We're on YouTube. Let's go watch other people do the calculation. Let me find someone who did the calculation. Okay, this is the Michelson interferometer. Let's do. This is just the Michelson interferometer. No, this is the Michaelson-Morely experiment. Maybe derivation, the actual math. 11 years ago, I watched this guy. I think this was okay. Oh, he just shows us. So he's not going to go through the steps. He's just going to splash it on the board. So he just says the time difference is d over c. What is d? 2 pi r squared. 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 What is d over? What is d? I don't know what d is. Let me see. What is d? D is this. Oh, that's just the distance to. That's one of the arm's distance. Assuming it's the same arm. So it depends on the arm. The okay. So let's assume D. Let's look at the result. Maybe we can intuit the result without the math because the result seems simple. Let's go here.
being in phase. This would cause an
So the time difference is D over C, wow, times V squared over C squared. So it's dV squared over C cubed. Fascinating. So the time difference is relative to the speed of the ether squared, but over the speed of light cubed. That's an incredible. And this has nothing to do with light. This is C water wave speed. So if this is water wave speed and this is the velocity that the water is flowing, this would still be true. So it's really interesting that that's the difference. The difference is so bizarre. It's V squared over C cubed. So C is the speed of the waves in the medium, and V is the speed of the medium through the apparatus. So it's V cubed over V squared over C cubed times D. Let's just take this equation. We can always come back and derive this and make sure this is correct, but let's assume this is correct. So it's dV squared over C cubed, right?
an interference pattern to be observed at the detector. If we keep rotating our setup, there would be a time when ether direction is horizontal and we should see the interference pattern. So we expect the detector to show varying intensities as we rotate our setup. But this does not happen.
Notice that they're not showing the proper result. That's not what happened. The dot doesn't grow and go away. See, they never ran, they never used an whoever did the animation never used an interferometer or never even watched a YouTube video where they play around with an interferometer. That's not what happens. What you see is waves inside waves. You see wavefronts. So it's going to be black and red, a bunch of like two or three circles. That's what we saw yesterday.
We can make two
That's not what you see. It doesn't grow and go away. No.
conclusions from this. Either the ether does not exist and light does not need a medium, or at the time we conducted this experiment,
I mean, maybe at the center, this is what happens. I don't know.
the ethers were
I mean, it makes sense. If you have one wave, either you see something and then it becomes, it goes, then you don't see it. If they completely destruct it, if it's complete destruction, then yeah, they would go away. But I think because the laser, when it comes out, I don't think for some reason, I don't know. I mean, what we saw on the wall yesterday, we saw concentric circles. So I don't know. This would make sense that you should see something like this. It should, but it shouldn't grow. I wouldn't say grow. Yeah, maybe that. Yeah, it should just be. It should fade away and come back. Fade away and come back. So you can just look at the center maybe and just see if it fades away and comes back. That's half a wavelength.
velocity relative to the earth was zero. But the earth is not still and it keeps
Yeah, unbelievable. So they just thought the ether is like cosmic wind, basically. That was their theory. They just they didn't know better.
moving.
So funny. And Michelson died
Let's
knowing that his experiment failed and he didn't know why. Oh my God, what a heartbreak.
wait for 6 months so that we can be sure the earth's velocity direction has changed and
Yeah, it never changes. Unbelievable.
conduct this experiment again.
I mean, you could get some flow. I mean, this could be a whole new way. You could use the ether like a telescope. So you could do like an ether telescope and just like detect. You could detect changes in the flow of ether that would indicate, right? So you could cancel the Earth, for example. So you can cancel the speed of the Earth, and then you would get the ether maybe from the effect of the moon. You can cancel that, and then you can get the ether, the effect from the sun. Cancel that, and keep canceling things until you get some noise, and then okay, that should be, the galactic effect, cancel that. That should be the cluster effect, cancel that. And then you'd get the universe effect. And that should be very interesting because it could be that you could notice, I don't know what. What would you notice then? This is so fascinating. You could see all sorts of effects. This is very similar to LIGO, but it's easier. You can do this from the comfort of your literal hand. You could have this device in your hand. This could be built into your iPhone. This could literally be built into your iPhone. Could be incredibly sensitive. And you could just, have a telescope, have an ether telescope. And you could walk on Earth and see how it changes. And so you could have a GPS. You could have a GPS. You could have a GPS because you can map the Earth, exactly what it looks like. Because certain places on Earth, there's like footprints. Oh my God, there's going to be a whole new. You don't need GPS satellites now. You don't need them because you can tell where you are. You have the map. Wait, yeah, yeah, yeah. You can basically, I don't know, you can't triangulate, but now you could have it in satellites, so the satellites would feel it. You could have these detectors in satellites. Anyway, it's like a whole industry, a whole new way of doing research. It's a whole new field of research. It's a whole universe of science. It's a whole new science. Wow. So this is the science of the ether. This is ether science. I can't wait to see a new ether, what do you call it? Like faculty. Like you look at the physics faculty, this guy does string theory, that. So it's going to be an ether. I'm professor, I teach ether. Intro to ether. There's going to be textbooks about the ether. And they're going to talk about me, but they wouldn't know how to name me. That would be so funny. That would be really funny. So there was this guy, and he did all these things. All right. Anybody? There's somebody watching. All right. Welcome. Welcome. Anyway, so after 6 months, yeah. But let's take that equation. Let's assume that this equation is correct. dv squared over c cubed. And then, for a homework assignment, you could validate or derive this yourself and tell me if it's correct. So dv squared over c cubed. dv squared over c cubed. Okay. dv squared, let's create a new page. A new page. New, okay. Okay. All right. Predict ether experiment. Oh, just enough. Okay. Okay. So time difference. So I would say delta t. Time difference. The time difference. How is that useful? Let's write it down. It's d v squared over c cubed. How does that help us? The difference in time. How does that help us? What do we want? Don't we want lambda? The time difference? What? Time difference? What do you mean time difference? What do you mean time difference? I don't know what you mean time difference. The time difference? Andrew, what's up?
Finally.
What fine? Oh yeah, I'm free. Yeah, I'm doing the. Are you math?
Yeah, kinda.
Okay, so I'm deriving.
Yeah.
So I'm deriving the experiment. I want to know. I want to be able to predict what are we going to see.
What type of math?
This is geometry. So
Sure. What type of?
uh,
Oh, geometry.
this is
Sure. Slide me a picture.
so just scroll away. Just scroll away from or just look at my stream. Go
Mm-hmm.
to my stream.
Yeah. Oh
You
no, 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 I have seen it. C equal dv bar 2 over 3 bar 3.
hold on.
All right. Let me see. Let me see your screen. Wait. I can see it. Yeah, I can see it. Type.
Okay, so they're saying that this is the time difference between the two arms of the interferometer. But
Mm-hmm.
how does that help me? Why do I care about the time difference? I don't care about the time difference. I want to know. I want to know what I want to know. Here, I'll tell you what I want to know.
Mm-hmm.
I want to know
Mm-hmm.
the
Wait. Can you open your screen?
which one?
Open your screen, man.
Which one?
Your screen. Share screen.
What do you mean? I don't know what you mean. Share screen. What,
Open your. No, share screen so I can watch with you.
I am sharing. What do you mean? It's being shared.
No, you're not sharing.
Where are you looking? Are you
Never
on you?
mind.
What?
No, I'm not looking anywhere.
So go to YouTube.
Wait. Oh, yeah, my bad.
No. The best thing is if you
I'm
go
gonna join you live.
watch me. The best thing is to watch the video on you. Can you watch on YouTube while you're talking to me here?
Nope,
Okay.
cannot.
Okay. Then you see this equation. This I got this from one of the videos
Mm-hmm.
on YouTube. So he says that you
Wait.
wait. What?
Mm-hmm. You can talk.
What?
No, I didn't say wait.
Okay.
I didn't say wait. You can talk.
Okay. So do you know what an interferometer is?
Yeah, obviously.
What do you mean? Obviously.
Yes, I mean yes. Yes.
How do you know?
You
You
just say yes.
no, but you know from what I explained, or you knew this from before?
No, I have know it in my school.
Oh, that's good.
Yeah,
So
thanks.
what I'm looking, I'll tell you what I'm looking for in order to predict this experiment. What I'm looking for is basically what's known as radians. I want to know, sorry, not radians. I want to know wavelengths or
Mm-hmm.
how many half wavelengths. How many times should the circles move like from high to low?
Wait. Is that wavelengths over two or per what?
No, it's half a wavelength. It's a wave front. So
Yeah.
right, so you
You
have
can just do
right. So
half the lambda.
from top to top is one wavelength. This
Mm-hmm.
is one
Yeah,
wavelength.
I know it. I know it.
So
it it's wait. It's either a
wait, is
crust or a trough.
this is a full wave, right?
Yeah.
So from top
Hold
to
on.
top.
Yeah.
Wait, so
Or
from
from
top
bottom
to
to
top,
bottom.
right? But because we have two waves, we have another wave that we're trying to right constructively and destructively interfere. So we have another wave.
Yeah.
So
Mm-hmm.
let me copy this. So we have another wave,
Oh.
and
Uh-huh.
what we're trying to do is we're saying, let me just take the wave. So we have another wave. So this way they're constructively interfering. So it should just be the original
Yeah.
laser dot. But now
Mm-hmm.
inside the laser dot, right? So now,
Mm.
well,
There's difference in the angle.
if we go all the way to here, now there's no signal. Now the center dot, now the dot is gone.
Yeah.
The dot should be completely gone. Here it should start fading away. So it should just it right if it's gone here, then it should be half faded away here. So it starts.
Mm. Right.
So it should start fading away. So it should start fading away, start
No,
and completely
no, no,
fade.
no, wait.
What?
The point is, they still share the same longitudinal.
What do you mean?
They have the same longitudinal. You know what longitudinal means?
No.
Longitudinal, when it comes to wavelengths, is basically the top or the crust of the wave. So they share the same crust, therefore they have the same trough.
It's the
So they
same.
are basically the same,
Yeah.
but in different angles, in
Yes.
different rotation, basically.
Yes. So
Yeah.
it's the same. It's the same beam split in two, and then
Mm-hmm.
let's say we calibrate it so it's perfectly aligned. So we have perfect
Yeah.
constructive interference, but this is just the original dot. So we split it in two. It's not even the original because some of it went away back to the emitter. I think we lost half of the energy we lost because of the way mirror. Hey,
But you can't calculate the energy which you lost.
what?
But you can't calculate the energy which you have lost.
Yeah, okay, half of the energy of the beam is gone. So half of the intensity we lost.
Maybe.
That's okay. But
Mm-hmm.
so now
Mm-hmm.
this is half of the original energy. Let's call this the original energy. It's fine. It's a dot. This is the maximum
Yeah.
dot we're going to get. Now as we start rotating the interferometer, that's what we expect, or that's what Michelson-Morley expect. They expected it basically to fade away, completely fade away, and then come back, and completely come back. So
Oh, yeah.
right, so we expect. I think we have to move by an entire wavelength, right? We start. This is an entire wavelength. We're moving by one. So if we throw this away, let me throw this away and copy it again. So if we copy, so it's not half wavelength. We need a complete wavelength.
Yeah.
So this is complete constructive interference, complete destructive
Mm-hmm.
interference. Half of a wavelength is complete destructive, and this is
Yeah.
complete constructive. So we need entire wavelength. We don't care about half wavelength. Okay. So so
Yeah.
this is incorrect. So let me move this out of.
Wait. Wait, it can be half a wavelength. They are just a replica. So if you separate them, it would result in a full wavelength.
Wait, I'm losing you. What just happened? Wait, did I just lose it? This is so funny. Okay, we'll come back to this. Oh, Andrew. Andrew with his terrible internet keeps dropping. His signal keeps dropping. Anyway, that was actually very useful. Cruise ship, do you want to talk? What is going on? Cruise ship, you want to talk? Anyway,
Very like, can you hear me? Okay. Can you hear me?
very badly. Your signal is horrible. You're roboting horrendously. But it's fine.
Oh,
It's fine.
uh,
It's fine. Go ahead.
I'll
Are
be
you?
right back.
Wait. What's going on? You're turning something. Oh my God! You dropped off too. Now you dropped on. You dropped on and off. All right. Everybody's dropping on and off. It's better than nothing. Anyway, so let's start this over. So what we want to discover, we want to be able to say we expect this many wavelengths per, I would say, per radian. Per radian. Is there a word for radian? I don't know. I think you usually just say radian. So how many wavelengths per radian or per degree? That's the question. What is radian, by the way? I think a radian is just easier to use. Let's look up what is a radian. Okay. What is a radian? What are radians? Cruise ship, what's up? Can you talk? Okay, if you can talk, I'll come back to you. Let me find this guy. Okay, so what is the radian? What are radians? What are radians?
Previous video, we looked at how angles are measured using degrees. This angle would measure around 30 degrees. A right angle would measure 90 degrees, a straight line 180 degrees, and one complete rotation 360 degrees. Do you know why 360 degrees? It's somewhat arbitrary and had something to do with the base 60 number system. Do we have some other way in which we can measure angles such that it makes a little more sense? Yes, that brings us to the concept of radians, and trust me, not many people understand what radians mean. Most people know how to convert from degrees to radians and vice versa, but it ends there. To understand what radians mean, let's draw a circle. Let point O be its center and length R be its radius. Now let me take this length R and place it here at this point. Now all I do is push it onto the circumference of the circle. The length of this red part is still R, it has just become curved, and that's all. The curved length R starts from here and ends here. Now, from the center of the circle, we draw another radius that joins the other end point of the red curve. This length will also be R as it's the radius. Let's analyze the figure. We have an arc of length equal to the radius of the circle and two radii joining the center and the endpoints of that arc. Remember, the length of the arc is equal to the radius of the circle. This angle formed here is 1 radian. That's the concept of radians. Actually, there's radius everywhere around this angle. R, R, and that's probably why they call it radians. According to various scientists and mathematicians, this is a more logical way to measure angles. It's because we're measuring the angle in relation to the radius of the circle. But how are radians related to degrees? What would this angle be equal to in degrees? If you understood the concept of radians well, then understanding the conversion between degrees and radians would be a walk in the park. What is the circumference of a circle? It's 2 pi r, where r is the radius of the circle. We are talking about the circumference, which is the entire boundary of the circle. Now listen to the next question well. How many such arcs would you need to cover the entire boundary of the circle?
2 pi.
Let me repeat the question. How many such arcs of length r would you need to cover the circumference of the circle? Pause the video and see if you can work through this on your own.
Pi is basically 3. 3 times 2 is 6. So it's 6 point something.
The length of the arc is r and the circumference is 2 pi r. Yes, 2 pi r. It means we would need 2 pi such arcs to cover the circumference. 2 pi arcs? What does that mean? As pi is approximately 3.14, we would need 6.28 arcs to cover the circumference. How would it look? This is 1 arc, 2, 3, 4, 5, 6, and a little part left for 0.28 arc or 28% of an arc. So we need 2 pi arcs to cover the entire circumference. And what does each arc correspond to at the center? We have seen that 1 arc corresponds to 1 radian at the center. It implies that to complete 1 full rotation, we would need 2 pi radians. And it tells us something more too.
360.
If we rotate 1 arm completely, then 2 pi radians will be covered at the center. But wait, hold on.
360.
We also know that 1 full rotation equals 360 degrees.
So it's 2 pi by
Yes,
360.
1 full rotation equals 360 degrees. As both equal 1 full rotation, these two will be equal. 2 pi radians will equal 360 degrees. That's the relation between degrees and radians.
Amazing.
This is what we have been working towards in this video.
Amazing.
If we understand this, we can easily derive the rest. This is 1 full rotation. Then how many radians will 180 degrees be
1
equal
pi.
to?
Pi radians.
If we divide this equation by 2, we get pi radians equal to 180 degrees. And 180 degrees is half circle or a straight line. And what about a right angle? If we divide this equation by 2, we get pi over 2 radians equal to 90 degrees.
Oh, that's good.
So a right angle is equivalent to pi by 2 radians. These three relations are most important when it comes to conversion between degrees and radians. And we don't really need to remember all three. Knowing just one is enough, and we can derive the rest. And now we come to the last and the most important point of this video. What does 1 radian equal to in degrees? If we divide the first equation by 2 pi, we get 1 radian as 360 over 2 pi degrees. Substituting the value of pi as 3.14, we get the approximate value of 1 radian as 57.2958 degrees.
Wow.
That's the degree measure of 1 radian. If we have an angle like this, which measures 1 radian, it will equal 57.2958 degrees.
Absolutely amazing. Absolutely amazing. Absolutely amazing. All right, let's.
It will equal 57.
That's good. That was good. That was good. So can't connect. Oh, so cruise ship cannot connect. Andrew is gone, and we are alone in this universe, in this expanding universe. Johnny Boy Darty, do you think the moon landing happened? Yes, I think it happened. If you think it did not happen, then, I don't know what to tell you. It's like, it obviously did. I mean, all the evidence points at it. Now, do I think it was wise to do it? No, I think it was a waste of money. It was basically $1 trillion in today's money. And it was completely wasted. There was no reason to do it. It was complete garbage. So the way it happened was, okay, so they said, let's do a moon landing. Let's create NASA. But just before they created NASA, they actually planned to build an actual atomic ship that Freeman Dyson worked on. A real atomic ship, not atomic engine, an atom bomb engine, an actual atom bomb engine ship that's like built like a submarine, like out of complete steel. Everything is steel, not thin steel, actual steel, like a submarine. And it would have been able to hold 150 crew members and travel all over the solar system. They saw the future. But then the president, I don't know who it was, he asked him, maybe Eisenhower it was, he asked Freeman Dyson, so the radiation, how many people is it going to affect? So Freeman Dyson did the calculations. He said 1 person per year is going to die because of the radiation. Literally, this is a quote. I'm not joking. You can watch the documentary. It's on YouTube. So they actually asked Freeman Dyson, what should we do? And Freeman Dyson said, we should shelve it. He literally said that. It was up to him. That's what he explained. It was up to him. And he said, shelve it. Anyway, let me just respond to a message. Okay, we got to do our work, so we got to continue. 1 second. Let me check something. Let me check. Let me check. Let me check. Let me check. Checking. Check. Okay. That's it. Good. It's good. It's good. The next step, what do you do when your heart is aching so much? What do you do? What do you do for a terrible, terrible heartache? Okay. Okay. Yeah, we want to go back to finding out what's going on. So, we looked at what a radian is. It's just our, it's just an arc. It's just an arc. It's a convenience. That's all it is. I keep hearing, like, the signal that somebody's communicating, but I don't see any communication. Oh, it's here. Goddess Ashley, say yes, Goddess, if you are below 6 inches and ready to be dominated by me. DM opens for subs. Goddess Ashley, interesting. Goddess Ashley. Femdom 28. I'm a cruel mistress of high class, trained in the old and professional way. That's very nice. But we're busy. We're very busy. Very, very busy. We're busy people. We're busy. Busy, busy, busy. I am a human. I am a human. All right, let's continue. So we want to be able to predict the number of wavelengths, which we would, this is what we'll see. We'll see wavelengths. Because wavelengths, you see the dot of the laser showing up, fading away, disappearing, and showing up again. Reappearing, showing up. So from showing to disappearing to showing, that's one wavelength. How many of these do we expect when we rotate, let's say 90 degrees? That's the clearest thing. Even though 45 degrees, no, I would say 90 degrees. So 90 degrees, how many radians is 90 degrees? Or we can just do 90 degrees because radians don't convert well. Or do they? 1 second, let me send the message, clear message. Hold on 1 second. I cannot talk. I cannot talk. Try as I might, want as I might, I cannot talk. My computer is so hot. It's such a waste of energy because it's so hot in this room in the computer. It's like, why is it getting so hot? It's actually costing a lot in the electric bill. This computer ends up being an expensive electric bill. Hmm. 1 second. One second. One. 1 second. 1 second. 1 second. Okay. So what we need to do. So how many lambdas? How many wavelengths? Jesus Christ! Let me use my laptop to answer messages. Very good. Okay. Let me check email because I'm expecting nothing. Nothing. Wow. I might just need to buy a new laptop. Maybe I'll buy the not the Macintosh, not it's called a Mac. Maybe I'll buy a MacBook. It should be like it shouldn't be that expensive. This laptop was a terrible, terrible decision. I mean, the previous one was like so much better, and then my keyboard started malfunctioning, and then I destroyed it, and then I took it apart, and it's in the garbage now. It was just the most perfect laptop. It always stayed cool. It never, hardly ever heated up, and this one hardly ever not heat up. It's always so hot. Why is it so hot? Why is it so? Everything should be internally. There should be almost no moving parts. Why is it so hot? Jesus, Jesus, help me. Wait, we have a message in our. We have a message? No. But this is interesting. I got a notification. So it notified me here. Happy to have a conversation about why you should be vegan. Sure. Can't follow speed changes. Okay, but that's not the message that I got on my iPhone. So what sent me? Oh, it's probably the Studio app. I wouldn't know now. No, it's the YouTube app on my iPhone sent me a notification that someone wrote, I guess in the messages, which is something that I need. I never know when people write. When people write here, when we get to this message, when people write these messages, I never get a notification. It's like, why can't YouTube sound a notification every time there's an incoming message? Well, how difficult is that? So I always miss all these notifications. Okay. So what I wanted to look at, where were we? Let me check. Let me check. Well, I wanted to answer these guys. Let me see what they're writing. People are attacking me. Okay, so we had now it's gone. Yeah, YouTube is such a disaster. Like, where can I see all the notifications? Can I go somewhere to see the notifications? Oh. 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 Let me just make sure there's nothing personal here. This was actually dangerous to click on. Yeah. Doesn't want to go back. Escape. You can't hit escape. Can't go back. There is no going back. What's going on? There's no back. So we click settings, and now we're doomed. I probably have to scroll all the way down. This is very, very dangerous. See, this is where I don't want to show my email. Promotional content and offering. I don't want to see that. Shared content. Notify me when others share. Mention, replies, activity on my channel. Recommended videos. Subscriptions. Notify me about activity from channels. Let's remove that. I just want to get notified. That's all I want. But do I need to save it? Oh, let's just not share. Let me share something else. Let me share. I have a Discord message. Accepted my friendship. Okay. Okay. Hi. I am streaming now on YouTube. Wanna join? Okay, so let me share. I'll share my YouTube so I can go and check my notifications page. Oh, YouTube general product updates. I don't care. Creator updates and announcements. Send me emails about YouTube activity and updates. Send me emails about family and product updates for YouTube or YouTube. No. So how do you? There's nothing to save. So how do we go back? There's no going back. That is so weird. And there's no way to save. So it's all auto save. I don't know what to do. How do you go? There's no back. Okay, account. I guess we just have to go back to YouTube and maybe just history and this one. Okay, let's. Okay, good. So what yeah, let me share this and let's. Oh, we can't see. So there's no way we can access those messages that we got. So there's just. Oh, I would have to go to my channel management and maybe see the comments there, but I don't know. I just don't know. Okay, doesn't matter. Let's continue. Let's continue. So we're trying to predict the number of wavelengths per basically degree that we move. But really all we want is just over 90 degrees. All we care for is pi radians. That's all we don't care for 1 radian, we care for pi radians. Pi over pi radians, right? 2 pi is a full circle, pi radians is half a circle. Right? We want to go from here. We want to go, right? So we have the interferometer. And we basically, the emitter, mirror, mirror, display, half mirror. So, right? So original, 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 back, back, back. This is right now, well, assuming again, ether flow is this way. So this would be a little bit slower and this would be a little bit faster. So it came out correct. This comes ahead. How much ahead? How many waves? How many wavelengths ahead? That's what I care for. So we have the delta T equation. Let me see. So we have so we have the delta T equation. We copy the delta T. We know the delta T. We can convert delta T. We know the speed of light. So we should be able to convert delta T into wavelengths. Or at least it should give us how, like, the distance covered. What distance is here? We want to know this distance. And then we need to know the wavelength. The wavelength is dependent on the color. The color of, so lambda is given. What is this lambda? This is a given lambda. So we want the number of lambdas. So we want the number of lambdas. Lambda is given by the color, basically, of the laser. The lambda is going to show up probably when you buy the laser. It says the lambda on it. But also you can use the interferometer to figure out the lambda with a micrometer. We saw the video yesterday. So we know the lambda of this laser. So lambda is given. We can say lambda naught. So we know the lambda. We're looking for n, and pi radians is given. So all we want is n. How many? So n equals what? So we don't know what will, but this is the experiment. But all that we're after is n. I mean, we want to predict n. So over pi radians, how many wavelengths? So that's just this distance. So we know delta t. We know the delta t between these two. So we do delta t times c. That gives us delta t times c gives us this little distance. So it's delta t. So delta t times the speed of light, or the speed of the waves in the medium, is equal to delta L, where delta L is this. This to this. Oh my God. Sorry about that. That's not my fault. Happens all the time. La, 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 la. I don't know why it happens that it drops. I think it's a bug, and the app refreshes. Whoever wrote it, it's his fault. Any water? We need more water. Water. La 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 la. It's so beautiful to sit on the shoulders of giants, to stand on the shoulder of giants. Like, everybody did so much work that all I need to do is just look at the end of a video. Here is this equation. Like, different people already did so much work. Now it's my turn to do some work. That's like, very few people have a chance to like contribute to, the history of humanity. Who did? I mean, very few. I mean, everybody can contribute, but like the big, like big moves. Who had a chance to do a big move? Very few. You could say like Newton did. Theoretically, maybe you could say Einstein did. Um, Galileo. Imagine I would be one of those great ones. That'd be so funny. It's just luck. I think it's a lot of it is luck. I mean, right? Because what created me? What created my intuition? Like, it's probably a lot of it is just genetic. Like like they say about Einstein, that he wasn't anything. There was nothing good about him except for his Gedanken experiments. That he was able to think through experiments, and I also have that. I'm not good. I'm not exceptionally good with anything else. I'm pretty okay with everything, but my ability to think through things, to even to just to come up with the idea that I need to think through something that no one else thought about. That's like, so like with black holes, like I was, for a long time I was able to imagine myself at the center of the black hole and slowly build, and build a thought experiment that I came up with my own thought experiment. Like, when I knew almost nothing about anything, I was able to put together a thought experiment, just to think of thinking of a thought experiment. Just the idea of, okay, no one has done this before, and it kept bothering me. What the heck is happening at the center of the black hole? And then it came to me, I could slowly create a black hole if I just go into a star in my mind, go to the center of a star, and now let's go through the steps. I'm at the center. I'm right inside the innermost particle. And what is it? Well, it's basically a neutron or a proton. Well, later it's going to become a neutron. And now let's pile on more and more stuff. So the neutron is under pressure, it compresses, and at one point, this compression, this is energy, and energy is mass. According to Einstein, I'm assuming he got that right. I hope he didn't screw that up. We'll have to come back. But assuming E equals mc squared, I have to assume that the mass of this neutron keeps growing. So ultimately, right, this just means it's interacting more and more with the Higgs field, with the not field, with the Higgs mechanism, which means it's just causing the collapse, the deterioration of the ether, which causes the ether. Basically, a vacuum is created. So a vacuum is created. I don't know where the destroyed ether goes. The fact that the ether can be destroyed and created out of thin air at the in the through dark energy, that suggests, it feels like they're connected. There's like a connection from every particle that interacts with the Higgs to somewhere else. It's like there's all these, it's like another dimension. So we still need to figure that out. Where does the collapsed ether go? Because it goes into, it keeps flowing into massive particles. It keeps flowing into okay, we'll come back to this, but also, how can we actually interact with the ether? It's like every device we build is the ether. How can we interact with it? So waves, yes. Any interaction is an interaction with the ether. Now that we know it's there, so gravity is a great way to interact with it. What else? How else? Well, we know like any energy interacts with it, like electric, like an electron is a disturbance, right? An electron is a wave, right? All the particles are just waves in the ether. Maybe they are standing waves. I don't know. Why is an electron attracted to a proton? How does that work as a wave? Why would this wave be attracted to that wave? What does that even mean? I don't understand it. It's like these waves are trying to move, but something is attracting them to each other. That's so weird. Why would waves? But maybe because of the interaction, they look to each other like particles somehow. I don't know. So, but I think that quantum field theory has already explained everything. I'd be really curious to hear what's the explanation. How do they explain the just electricity, just simple static electricity? How is that explained? What does an electron look like to in quantum field theory? What does it look like? Like in a particle accelerator, it looks like a particle, but that's just the interaction. That's instantaneous interaction. That can't be. It can't really live as a particle. It looks like a particle when you instantaneously interact with it, but then it's back to being a wave, according to my theory. Anyway, so delta t times the speed of the waves in the medium is equal to delta L. This is delta L. So we go like this, like this. This is delta L. Okay. So delta L. Then how many wavelengths are in this delta? Well, we need the wavelength. So delta L divided by a wavelength. Again, delta L divided by lambda naught, an actual single wavelength, that's n. That's the number of times, and that's what we're looking for. That's the number that's what we expect to see. All we expect to see at the lab is to be able to count n times that the dot shows up, disappears, and shows up. From showing up to showing up as we rotate the device. Now we know that red light, we saw the video yesterday. Did I remove all these videos? We saw a video yesterday. Let me open a new thingy. We need the wavelength of a red laser. So in my history, we should be able to see the experiment. One of these, but we saw so many experiments. It was the first one. The first one. No, it wasn't this. It was a similar one. Maybe this. No, that's not the apparatus that we saw. I think this is the apparatus, but why isn't it changing? This one. So in this one, they calculated, oh, it's red light. They counted, calculation, it's red. There it is. Red. So red is 0.65 micrometers. So red is 0.65. Let's assume red is 0.65 micrometers. So lambda, red, is equal to 0.65 micrometer. Is this how you write micro? No, it's the other way. Here, let me show you. See, micro is it's like a U, but with the beginning is elongated. Okay. So undo, undo, undo. So it's micrometer. Okay, assuming lambda naught is defined, assuming it is lambda red, so it's 0.65 micrometers. That's the length, that's L. So let me check the message. Message. Okay. So whatever, now do we know delta L? So can we calculate delta? Yes, delta L we can calculate. We should be able to calculate the whole thing. Okay, so delta L, so let's start plugging in. So we want any, what was that? Nothing. Okay, so let's start again. So N is what we expect to see at the lab, and it's equal to delta L that we can calculate divided by lambda naught. Okay, so lambda naught is 0.65. So we know lambda naught. Now what is delta L? So delta L is equal to delta T delta C. So delta L is equal to delta T times C, not delta C, times C. We know C. C is famous, 300 meters, 300 million meters per second. What is delta T? Delta T, we know, is D. Well, D we'll have to plug in the lab. So it's D V squared. V we know, we calculated 6 million meters per second. And again, C cubed we know. So delta T is dv squared over c cubed. So it's equal to d, we'll plug in, that's the arm, that's the interferometer arm. dv we know, but we'll plug it in towards, I mean, maybe, okay, soon we'll plug it in, over c cubed. But we have to multiply this. This is delta t. Delta t, this is nothing. Delta t times c. Okay, that's delta L. So that's delta L. So obviously, c cancels out, and this becomes c squared. Okay. That's delta L. But we need to divide by lambda. Okay, so we need to take this. Let's take it, copy it to the next page. So let's take this, copy, and next page. Okay, I think we're almost done. So this is the experiment prediction. Very nice. Okay, so paste. And draw a line. Okay, so we just want n. So n is equal to the prediction of number of times the dot will appear and disappear as we rotate about pi radians. This is for pi. Everything we're doing is for pi radians. This experiment is going to be over pi radians. So it's delta L. So this is delta L. So let's plug in. Delta L is D times V squared over C squared. So this is delta L over lambda. So over lambda just means we plug in lambda here. And I'm assuming, well, this is the equation. This is for pi radians. Meaning 180 degrees. No, 90 degrees. Wait a minute. No, it's pi over 2. This is pi over 2 radians, meaning 90 degrees. So this is for pi over 2 radians. This is, we just keep in mind that when we perform the experiment, we should rotate 90 degrees. And over the process of 90 degrees, we should count n. N should be dv squared over c squared lambda. So let's plug in some rational numbers. So d is how critical is d? I mean, right? The bigger d is, I guess, right? The bigger d is, the bigger n is going to be. And the bigger n, the more accurate, the more accurate this whole thing is. But assuming some d, I don't care. Let's assume it's going to be. I saw these devices, these interferometers. They're about 20 centimeters. So we can plug in just to get a rough number. All we want is a rough number at this point. So rough numbers. So let's say D is going to be about, let's say D is from the mirror, because we saw D. What is this D? So I looked at D. It looks like D is, what is D? It's not clear. The mirror, but what is this? He doesn't say. Let me see. What is D? What is D? Okay.
To be precise, this is the time taken for the horizontal wave.
There's D, but he doesn't say what D
And this is
is.
the time taken. This is the time will get deflected towards the direction of the ether. Vertical wave which
The question
crosses
is this D? Is this D? I'm assuming this is D. D is just from the split beam splitter to the display. That's my intuition.
no resistance but will get deflected towards the direction of the ether. To be precise, this is the time taken.
So this is a mirror and this is the display. Which mirror? Which mirror? It should be this, the beam splitter. So the mirror is here. Wait, I have a phone call. 1 second, let me mute you guys. 1 second. Oh, it got disconnected. Who was that? That was weird. That was a weird phone number. What was that? Oh, it's from a weird country. It's a weird country. Wait, I have 2 voice messages? I don't care. So what is D, Jesus? He's not telling us what D is. So this is useless. We need to find someone.
Taken for the horizontal wave.
So it says here,
Ether.
time is distance traveled over speed. What distance traveled? So D over C plus V plus D over C minus V. Okay. That it looks like it's from the half mirror to the display. Right? He says go there and back again. So if we look at our diagrams, let's go back to one of our diagrams. I think this one. No. This one. So it looks like escape. 1 second, message. Wait, we have a message from 27 minutes ago. Yeah, that's fine. I don't care. Is it on? Yeah. So remember that this is right there and back again. Because here they travel, this is the difference between them. So we want to calculate this relative to this. So how much time does this take and how much time does this take? The question is it critical to know the precise D, or are we just assuming? So we need to assume that these Ds are identical. That has to be an assumption. Otherwise, our calculations are going to be off. But it doesn't matter because I don't think I think this can be approximate because it's an approximate n. It's not the n is not super critical. Whatever the so it's fine. So it's just this is D. I'm assuming this is D. So D it's from the mirror to the splitter. This is the difference between them. After this, they both suffer the same consequences. So that's not a symmetry breaker part of the experiment. The only symmetry breaker in this experiment is this relative to this. So and these should be identical. So the only thing we should be playing around with maybe when we run this experiment is the emitter or one of these, but you want to you calibrate it. It doesn't matter. Anyway, I don't think it's critical that it's exactly something. It's approximate. Okay, so let's go back. So we're assuming D, it doesn't matter. D is from the mirror to the splitter. Splitter mirror, it's from the splitter to the mirror and from the splitter to the mirror and back to the mirror. Okay. So D, so if we draw, let's just draw it here again. So this is the apparatus, the emitter, the beam splitter, mirror, mirror, and display, the final display. So either this is D or this is D. So let's assume that this is D. That's D. Let's magnify this a little bit. Okay, that's D. Good. So now what? So let's just plug in some D. Let's say D is, let's say D is equal to, I'm assuming 20 centimeters from what I saw. Let's assume it's 20 centimeters. Okay, that's D. Okay. V is about 6 times 10 to the 6 meters per second. That's V. C squared, we know. Let's write it down. And lambda, we know. Lambda we said is point, it's not here. Lambda was like 0.65 or something. Where is that? Of course. Lambda is 0.65 nanometers. Nanometers? No, that's micrometers. So it's 0.65 micrometers. So lambda is 0.65 micrometers. Well, what's a micrometer? A micrometer is 1/1,000th. So it's 0.65 divided by a million. Okay, we'll come back to this when we do the plug-in. So dv squared over c squared lambda. It's very difficult to write on this paper. So much more convenient. So okay, let's start plugging in. So d, so n is equal to, well, d is 20 centimeters. So 20 centimeters. That's d. D v squared, v is about 6 times 10 to the 6 meters per second. This is squared. dv squared over c squared lambda. C squared is 300 times 10 to the 6 meters per second. So c squared times lambda. Lambda is 0.65 micrometers. So let's do 0. Oops, 0.65 micrometers. Okay. Okay. Oh my God. Drawing with the mouse is very painful for my hand. I didn't know it's so painful. I never wrote so much, never drew so much. It's so difficult. Okay, so let's cancel out some, at least units. So, well, meters per second squared and meters per second squared go away. Even, yeah, they go away. Meters and meters go away. So all we have here is micro, which means divided by a million, and centi, which means times 100. So it's 100. No, centimeter is 100th of a meter. So we basically have So we'll come back to this. What else can we? Okay, so 10 to the 6 squared and 10 to the 6 squared go away. 0 squared and 0 squared. I think these should, it's like times 10 squared times 10 squared. So this 0 with this 0 goes away. What else do we know? We could say, no, we can't. All right, what else do we have? Okay, so let's take this and go to the next page. I don't want to draw too much. Let's take this, copy, create a new page. Calc cont. What did I copy? That's the wrong thing. That's not what I wanted. Copy. That's good. Okay. Okay. So now centi means divided by 100. So we need to put 100 here. And micro means divided by 1,000,000. So we need to put 10 to the 6 here. Okay. So we have 6 zeros at the top. So let's drop 2 zeros and we're down to 4. What else do we have? So there's 4 zeros here, and there is, well, this is 100 squared is also 4 zeros. So this is 10,000 and this is 10,000. So it goes away. Okay, so a lot of things went away. We just have a few numbers. And don't forget that the 6 meters is a very ballpark figure. So basically it's 6 squared times 2. So 2 times, so let's go to this color. So 6 squared is just 36. And 36 times 2, 36 times 2, 72. But this is ballpark, so okay, whatever, 72. And 0.65, what are the units? We don't have any units. Yeah, because it's a number. That's good. So all the units got canceled out. That's a good indication that we're on the money. So we have 72 divided by 3 times 0.65, which is about, let's say, 0.7. 3 times 7 is about 20. So it's 2 because there's a point. So it's 2. It's basically 2. 72 divided by 70 divided by 2 is about 35. So we expect approximately 35. Wow, that's a big number. But it's not irrationally big. But that's, that's over 90 degrees. So that's that's a sort of expectation. So just be aware that that is basically the number that we want to. That's a ballpark. Basically, I would say between 10 and 100. So it's not 1,000, not 1,000,000. It's something rational. It's something that is, it makes sense. But that's the number. All right. That's it. That's the number we were after. So the next step is to do the experiment. So we have an expected. Now we need the actual result. So, well, it's now summer, so all the schools are closed, so we have no access to. All right, what is it's okay? We've been here for an hour and 15 minutes. Okay, so what is you? Okay, I think it's just another elaborate hoax. Yeah, it's not a hoax. I might be wrong. I'm not hoaxing anyone. I mean, everything is completely transparent. What hoax? I'm not taking any money. I'm wasting my time. I took off time from work to do this. So what do you mean hoax? I mean, Einstein was a hoax. There is no length contraction. That in itself is a hoax. It's obviously it's just an optic illusion. Obviously, that is so ridiculous. That I can tell you without looking too deeply into anything. There's so much nonsense in Einstein's relativity. But it's very interesting, Karabo, that you think it's a hoax. That means at least you understand what I'm saying. Wait, why are we seeing? Oh, I'm sharing the wrong. I was sharing the wrong. I didn't show my work because I was sharing the wrong. Anyway, let me show it to you again. Let me see. How long have we missed? How long have we been missing? How long has it been since I was showing you the proper screen? Oh, this is terribly terrible. So all this time that I was talking, I wasn't showing you my work. All the cancellations, I didn't show you all everything canceled out and I didn't show it. Okay, so I see where I last showed you something. It's when I went to check. So I see I went to check that it's red, that 0.65 is red, and I never came back. So I need to show you from the time that basically I probably wrote lambda. So let me show you again. So from what? Oh, it's you never saw me even starting this page. Oh, let's go to the previous page. I'm sorry. I'm sorry. Somebody has to be with me to tell me that I'm not sharing the right page. It should also, I wish it would just switch automatically. So calculation, I think we were here. Right, I think we were here. So lambda is 0.65. Okay, and then the last step was plugging in. So n is equal to, we said dv squared over c squared lambda. So lambda is 0.65 micrometers. Assuming the arm length is about 20 centimeters from, we said this is D, it's from the splitter to a mirror, either this or that, it doesn't matter. They have to be the same, but well, the accuracy, I don't think the accuracy is important. And then V squared, we're assuming about 6 million. We need to redo this more accurately. Maybe that should be the next step. But I can't do it with my hand and the mouse. It's too painful. So somebody else needs to do this. So 6 times 10 is 6 times 10 to the 6 meters per second is the v, the velocity that we calculated from Newton. So using Newtonian gravitational vector field equation, I derived the velocity of space at the surface of the Earth, 6 million meters per second squared. And then c squared is 300 million meters per second squared. And lambda is 0.65 micrometers. Okay, and then we canceled meters with meters, meters per second squared with meters per second squared, 10 to the 6 squared with 10 to the 6 squared. 0 with something. I don't know with what. Who knows? How did I cancel this 0? Is that a mistake? So we have one more 0 in the equation. So meter with meter, and we did this, it doesn't make any sense. So there's this 0. I don't know why I canceled this 0. So it's going to be 350? That's going to be very difficult to notice. And why did I not cancel this 0 with one of these zeros? So that was what I intended to do. We need to redo this. Let's start over. So I think we copied this to the next page. When the next page it's already ruined. So let's copy it again. Let's do this again. So wow, it actually ended up being good that it's a fortunate mistake that I made, because this 0, I don't know what happened to it. So let's just copy it to a brand new page. I got to run to the bathroom, but we need to do this. So fix 0 cancellation mistake. Okay, what do we got? So I don't know where this came from. So let's do this again. I don't want to make any mistakes. So start over. Okay, get rid of this. Start over. This is going to be our original. So let's take this again, the clean version, and put it here. Okay, so we're going to keep the clean version clean. So let's start canceling. So right away we see 0 with 0, meter with meter, meters per second squared with meters per second squared, 10 to the 6 squared with 10 to the 6 squared. This is not correct. This is 0 with 2 zeros, so you cannot do that. I just noticed that. Jesus. You have to be very careful. So we cannot do that. So, but what you can do is, well, for now, leave it. So the next step is to take the micro and bring up a million. Micro is millionths, so it's a million at the top. So we'll use it. So micro is 10 to the 6. So we have 10 to the 6 here now. And centi is per 100. So we have 100 here. Okay. Now, 0, okay, so we can do 0 from this and 0 from this. Oh, so it's going to be, okay, let's see. We'll see. I don't know. So 10 to the 6 and 300 squared. So this is 100 squared is 10,000. Okay, but this is 10 to the 6. So let's just go one more 0, and this goes to 5. That's too big. And this 6 becomes 5. Okay. Six times 6 is 36. This becomes 36. And we're done with this thing. 36 times 2 is 72. So we have 100 squared is 4 zeros, and this is 5 zeros, so this is just 10. 3 squared is 9, so we have 9, and this is finished. 9 times 0.65 is basically 10 times 6. 10 times 6 is just 6. So this and this is basically 6. 72 and 10 is 720. 720 is basically 600. And 600 divided by 6 is 100. So it's just 100. So this time we got 100. Wow, even a bigger number. So we need to know exactly, we need to get more precise numbers because we're all over the place. 35, 100. Still, it's normal numbers. 100, that's a lot. Imagine rotating it by 90 degrees. That means more than one per angle because it's 90. It's 100 per 90. It's basically it's one per degree. So it's one, let's call it, we can call it a wavelength per 1 degree. So for every rotation of the device by 1 degree, you're going to get a beep. You're gonna see a wavelength. You're going to see it. It's a complete interference cycle. So it's for every degree a complete interference cycle. That's a lot. That's going to be very difficult to notice. So what if we had a bigger arm? A bigger arm would make a bigger number. A bigger arm is even more numbers? I guess because in a bigger arm, the difference between the two arms is more exaggerated. Yeah. So you're gonna get more? Shouldn't it be the same? Shouldn't it be the same regardless of D? I mean, the bigger the arm, the more it ticks, the more ticks you get. So a tiny arm, you get, I guess, because in a tiny arm, it doesn't have much of a chance to get it to for the difference to grow. Over the bigger arm, the difference grows, and you just have more and more and more wavelengths, right? You just have more, and the bigger the number, I mean, you're just measuring, right? The prediction is the velocity. The whole prediction here is the velocity of the ether. We're just trying to predict the velocity of the ether. So you really need to know the velocity of the ether before you start this experiment because you wouldn't notice it. Like you really, like with a big arm, like the one that Michelson was using. Michelson and Morley were using huge arms. Those were, I would say, at least a meter. Imagine they did that vertically. We are having 100 for 20. So let's say it's 2 times, 3 times. And we're getting 100. They would get 200, 300. So per each angle, you really know, and they weren't using a laser beam. I don't even know what they were using, what kind of light source they had. This is 1886. They're probably using a candle. How would they even rotate with a candle? I mean, the candle itself shifts location. Oh my God. I mean, oh, but that part doesn't matter that it shifts, does it? What's going on? What's with all the refreshing? Jesus. Okay, but that's, we know where we're heading, but it's, we can do a more and more accurate. Let's maybe next time, let's do a more accurate, and then we can leave out. We should get our V straight. The next step we should try and get our V as accurate as possible, much more accurate than now. Uh, I don't think there should be any relativistic effects because we're measuring light waves. Light waves don't experience relativistic effects. They only experience Michelson effects. This should be the Michelson effect. This is the Michelson effect. So Michelson was looking for the Michelson effect. He couldn't find it. So no one ever named this effect after Michelson. But now it's time to name this effect. This is the Michelson effect. It's when you take an interferometer and you detect the difference between different angles of the two arms. That's the Michelson effect, or Michelson and Morley effect. I don't know anything about Morley, but I know Michelson. He never gave up. So we need to give him credit. Jesus. So this is the Michelson effect. So the Michelson effect. Well, what was I going to say? Yeah, I don't know if he had enough of an accuracy to actually have seen it, even if he would have done a vertical test. He would have had to do it like for every degree tick. You need to see the thing clicking. With those huge arms, that means not one, not two, probably 4 or 5 in 1 degree. That's imperceptible. You need to move it like 1/10 of a degree to see it clicking. But it would have, right, he should have been able to see it. Wait, what are we talking about? What are we talking about? Are we doing the right calculation? I'm thinking about it. 1 second, 1 second. I think we did the wrong calculation because we want to compare ticking from this position to that position. So when we rotate the interferometer by how many degrees? Right, we're talking about 90 degrees. So it's this arm, right. So we expect the two arms to shift. So over that, we should expect the difference to disappear and reappear. I think so. I think it's over 45 degrees. I think it's even more. Over 45 degrees, we expect this end, right? Okay, I need to go to the bathroom. Maybe I'll eat something and then I'll be back. We need to go through this thought experiment again and again and again. Make sure all our ducks are in a row. We cannot make a mistake. We need to be very, very diligent, very conscientious, very accurate, very, measured, step by step, get everything right. It would be nice for someone to look over my shoulder, see that I'm doing the right calculations. It's really very simple. I mean, this is lab work at this point. So laboratory, they just take the theory, take the prediction, and then they plan the experiment. Okay, based on the theory, let's plan the experiment step by step. That's usually the job of the experimentalist, I would say. The theoretician, he just comes up with ideas, and then He stops just at the point where, okay, now somebody else needs to put together an experiment. But I thought of this experiment. I mean, somebody else should have thought of this experiment, but I thought of it. I thought of it, so it's fine as long as nobody is as nobody's following my footsteps. I'll keep going. If I'll do all the work, so be it. It's just more credit. It's whatever. It's just credit. It's nice. It's it's like when you have a chance to make more money, you just make more money. Why not? That's all it's about. All right, let's take a break. So we've been here for 2 hours. We'll take a break and we'll continue after the break. All right, everybody. Thank you so much.